Hello friends and welcome. So, if any of you have done any research into direct coupling, you might have come across the connection that is usually associated with, which is called Loftin White. And what you'll see online if you read the comments is that you're probably being advised not to do it because it's inherently unstable, and if you blow up your driver tube, you'll blow up your output tubes and so on. Now, what I'm going to do in this video is present you with 4 types of circuits, of which 3 are completely safe to implement with direct coupling, and 1 is safe depending on how you do it, which is the standard Loftin White, which also can be made pretty safe. At least it won't be good if a tube fails for the life of your tube. However, it won't blow up, so it's not as bad as, for example, a fixed bias going missing. So that's what we're going to do in this video. However, just a side note, I am going to talk a little bit about some of the aspects of the circuit and why you would use it, but this is not a video about why you should use direct coupling or that you know sometimes just shifting capacitors or so. This is just assume that you want to have direct coupling. You want to have some of the possible circuits in your toolbox to make your amp, or choose your amp, or have an amp commissioned. So that is what these 4 circuits are for, so you have an idea. And also we're going to do a little bit of simple calculation so that we know how much the tube is going to stress out if the circuit fails. Alright, let's get into it. The first one is a cathode follower driving 2 output tubes. Now, this circuit is used a lot in high-end amps where you have dual output tubes, which means you got a PSE, so a parallel single-ended, or any parallel setup. It can also be push-pull even. In those cases, you want to use a cathode follower, and the reason why you want a cathode follower is that usually what you'll get is when you have these two tubes, even when they're reasonably matched, it seems that one of them is picking up the transient response and the other gets very lazy. Now, that probably has to do a little bit with how the grid charges up and then the interaction between the two things. But when you have a cathode follower driving it directly, what is happening is that this cathode follower has feedback, degenerative feedback here between for the grid, and that just means that the output is really following the grid regardless of what's happening. So if there's a little bit of grid current following, or there's more differences in capacitance here, this will make sure that the output is what it needs to be. So the grid of these tubes are being manhandled. Now, if we imagine ourselves that we want to, for example, bias 2 300Bs at minus 84 volts, that's what this circuit here represents. This is one way how we're going to go about it. Now, if you look at high-end amps like Kondo, so that's Audio Note Japan, if you will. If you look at the Kondo and Gaku, any Kondo, what you'll see is this type of circuit, but the only difference is that this usually is a negative rail, and you won't see a choke-loaded cathode follower, although I think this is pretty desirably sonically. And you won't see a cathode bias on the tubes. You'll see this is usually negative by fixed bias using a negative voltage rail. However, what I've done is a choke-loaded cathode follower and 2 300B output tubes, each separately finding their balance as far as bias is concerned, but driven by the cathode follower. Now, in this case, of course, if the cathode follower would fail, that tube would fail, nothing is really going on, because as you can see, there's a direct path here to ground. So the grid is then to the ground, and what really happens is that instead of minus 84, we actually got minus 87 volts and bias on the tube. So really, if this somehow fails, despite being directly connected, nothing is going to happen to your amp. This is super stable. It's also because of this driving characteristics, you'll drive these two really well. Now in particular, the 300B has a very dense grid, so there's very fine wires running a reasonable amount from or distant from the filament, and that means that is very dense, and because it's quite dense, thin and large, it has quite a high capacitance. So with that high capacitance, having the cathode follower driving it directly with very low output impedance usually means that grid is doing exactly what the incoming signal is doing, and because of the power delivery and the output impedance, you'll waste very little of your incoming signal to the capacitance of the grid. So that was example number 1. Very stable, excellent characteristics, no problems if the tube fails, no problems whatsoever really in this tube, even if your wire disconnects, no problems there. Another big advantage here of this type of circuit with the choke is, and this is a characteristic when I was studying a lot of top designs, so top circuits for top amplifiers, one of the things that all those amps had in common is that they had a very low grid to ground impedance. So, and when you're employing, well, the other thing was that they were DHT, so directly heated triodes have a tendency to start where the grid starts conducting as soon as you get anywhere near class A2 operation. So once the grid starts flowing, you can see that rather than going here, there will a part of the current will actually flow through here, and having only a choke to ground means that you almost can't get any lower in grid to ground impedance, and that is a characteristics I've seen in all high-end amps that are really, really well rated, that they have relatively to other amps a very low grid to ground impedance. So it also gives you a lot more headroom, and that headroom will be more stable. Its overload will behave much more quickly and recover more quickly because of this. So that's circuit number 1. A no-brainer. This is definitely one of these situations that you don't want an interstage transformer, you don't want cap coupling, that will all be very ruinous to the sound. This is really the way to go. Alright, now let's go over to circuit number 2. So, circuit number 2 is called direct reactance drive or monkey circuit, or full monkey circuit, depending on how this is actually exactly organized. Now this circuit is also super stable like number 1, however this is a proper directly coupled circuit that has no flaws. Whatever tube would fail or something, it is really stable, can't overload the tubes, nothing will blow up in this circuit. Now the way it works is that the two triads are basically stacked on top of each other. And I'll just explain that way, how the current flows, how the second tube gets powered. So we only have one B+, which is an advantage, but it needs to be higher. So it goes through the output tube. Say this is a 300B, could be 60 milliamps, 350 volts. So we got about 550 volts here to 600 volts. And then if you compare it to this one here, so this cathode bias resistor actually now sits here, and the bypass cap sits here. Right? This keeps the bias, the level stable, and here it keeps it stable here. Now, some of the voltage also gets dropped over this choke, so the power to the second tube goes like this, and the rest goes to the ground directly. So we're balancing these out. Its circuit is reasonably self-balancing, but it means, for example, that most of the bias comes from this dropping resistance just as it comes here. So in this case, in this example, we're biasing the 300B again at minus 84. However, we're dropping about 10 volts over the choke, which is the anode choke for this for the driver tube, and we're dropping 74 volts over this resistor. That means that if you look at a failure condition, that when this tube disappears, what we got left here is really that we have minus 74 volts bias in this circuit, and that means that instead of minus 84 we have minus 74, which means the current increases a little bit, which also means that the voltage over this resistor rises a little bit, so it will be a bit higher than 160, it will be a bit higher than 234, which reduces the bias even further, just because the increased current will compensate a little bit. So another nice aspect of this circuit is during startup of the amp. So this amp will not, this tube will not start conducting, getting power until this tube is ready. So as this is powering up and starts conducting, it will actually slowly increase the power to this tube, and this will start amplifying signal too. So this signal won't be full on driving this tube unless the tube itself is actually ready with and starts conducting. Otherwise, I don't think there's too much to say on this circuit. Oh, there's one more thing actually, what is very nice about this circuit. If you look at the supply impedance, so a lot of amplifier circuits will actually have a resistor as load for the driver tube, and it will also, that resistor, if you look at how usually there is a dropper resistor from the B+, and that means that the supply impedance to this tube is actually really low. The capacitor is fed through a dropper resistance, which means that the supply impedance of the driver tube is relatively high. In this case, what you'll see here, because we got say 60 to 80 milliamps from the 300B running here, that means that this capacitor here that keeps the B+ stable for the driver tube has a lot of supply current, which is relatively to most amps has a very low supply impedance. So that means that if this gets depleted a little bit, being drawn with the voltage swings from the driver and driving the output tube, it means that this can recharge relatively quickly and doesn't spend much time in a charging mode. So you have to sort of realize as you draw on current through this making demands, while this capacitor is charging, the sound will be different than this capacitor is fully charged. So this circuit, and I know this from subjective experience, this circuit relatively sounds dynamic compared to a lot of other circuits. We'll get back to that principle later in example 3b. So now we get to circuit 3a, which is the Loftin White. This is your classic directly coupled circuit, which a lot of people online will say is unstable. What I'm saying is it depends. So this really depends, and it really depends on the voltage difference between that is over the tube versus what is over the cathode resistor. So again, this cathode resistor is used to elevate the bias point enough so that we actually develop the correct bias. We have two B+ supplies, sometimes they're the same, but and here is usually a capacitor. So let's say, for example, we got 300 volts over here, we got our load, and then we got our driver tube, and it's directly connected to the output tube. Let's imagine in this case that we're driving a 2A3, and disregard these voltages a little bit. It's probably more realistic to have 40 volts bias and about 250 volts over the tube, and we're drawing 45 milliamps, so that's one of the good working points for a 2A3. So let's go with that. So we have got 130 there, and plus 250 is 380 volts over here. Now, what people will argue, in some ways correctly of course, that if this tube disconnects or fails, which is usually with, of course, the nice thing with tubes is they don't fail with a short, they usually fail with an open circuit, which is nice, a change from solid state. When that happens, the full B+ is actually comes on this thing, and this is of course what people imagine that happens when that it will blow up this tube, but we can work this out and actually start investigating what it actually starts doing. Because, so if 300 volt is here, then given a cathode voltage of 130 volts, gives us a bias of plus 170 instead of minus 40. So that looks quite dangerous. But what is really happening? So this is the question that we can ask ourselves. And the best way to do this in all of these directly coupled circuits is to imagine, this is how I would work at least, is to imagine that the current doubles. And then sort of let's, as it rising, what happens? So let's say, instead of the 45 milliamps that we had going, this becomes 90 milliamps. So that means we have the same resistor, double the current. That means that the voltage must be doubling. So what that means is that we have at 90 milliamps, we will have 260 volt here at the cathode, and we still have our 380 volts at the anode, at the plate. So that means we got 120 volts at 90 milliamps. So we got 120 volts over the tube and 90 milliamps running through it. Now let's look that up on the curves, right? So I've plotted it out for you. So we were here, and now we're here. Now, this is not good for the lifespan of the tube, having 90 milliamps running, but as you can see, we're still under the dissipation limit of a 2A3, which is 15 watts. We're still under it. So what we're moving towards to here is in this region. So because we got a heavily positive bias, we had plus 170, but because we were at plus 130 and we doubled it to 130, so we're now not at plus 170, we're now at plus 40. So what my expectation is, for example, if we triple the current, we're going from 45 to 135, and then we have 390 volts, but we only got 380 volts at the plate. So we can only maximally, the situation that we maximally can get here is that we're reaching 130 volts somewhere out here, and that this is absolutely near the cutoff of the tube, so we won't actually it won't actually increase at some point. So now, as you can see, this is still less than 15 watts because the voltage will just keep dropping really over the tube. So it will conduct, there will be a high current, but not enough to instantly blow up your tube. Yes, it will not, it's not good for your tube, but it won't blow up your tube. So, and why is this? It is because of this cathode resistor. Now, if we had put this cathode resistor for some reason at 200 volts and we had then 450 volts on the plate, this protection would have even been better, because after doubling we would be at 400 volts, which is then, we only have 50 volts then left. So the more we can actually increase the voltage here of the driver relatively, so especially if we would halve it, so we give half of the voltage available to the output tube and we give half to the driver tube, so we split it exactly in half, we would have a pretty safe circuit where if our operating point is not too high, it will always remain under this curve easily. And if we do half, that means that we only maximally have twice the normal bias current, the quiescent current of this tube, even in the worst case situation that this fails and complete or gets taken out. So there you have it. Loftin White, not exactly healthy for your tube when the driver tube fails, but it's not unsurmountable. And if you choose your values right, and or the driver with the output tube marry so that you can actually increase this voltage quite a bit, you're getting a better and better amp as far as your output tube surviving without, just by the passivity of the tube, so without sensors, without steering mechanism, servos and so on in your amp, it will already sort of self-protect itself, which is already better than fixed bias in a way, because if your fixed bias disconnects, you're in all kinds of issues, because the voltage was already, because you don't have the compensating effect of this bottom resistor. So that's Loftin White. It can be made reasonably safe, at least not to the point where your tubes blow up, but it depends. You need to do a careful implementation, and you just need to work. What I would always do is just double the current and see where you end up. If you end up in a place that you find acceptable and the headroom here runs out, you're in good shape. You can still do it. And else you might actually want a variation on this circuit that I came up with, based on some inspiration of course from others, but that's what I'm currently running, and we're going to that now. So here we got our fourth circuit, and I don't know what to call it. I haven't given it a name yet, but it's a sort of a variation on the Loftin White in a way. So that's its closest relative, but I've rejigged it a little bit, and it has some dynamic advantages in the way that this amp sounds. It's also way more stable than this, so it approximates this type of stability a lot more. So what is the basic idea of this? We got the same Loftin White, however, what I've now done, I've now introduced a situation we only have a single B+, and in my, by the way, in my Type 50 amp, this is the input tube, that's the driver tube. So here you got the 4P1L, and here you got the 46, and then we got driving the 50 via an interstage. Or you have a two-stage amp and you just drive everything directly. It really doesn't matter. Now, the way it runs here is we've got a dropper resistor here. So the technique that I'm using here is that we're feeding the majority of the current goes via this dropper resistor to ground. So that means, for example, if the driver only runs 6 milliamps, that for example the dropper resistance runs 3 times as high, for example at 80 milliamps. But we can also do 4 or 5 times higher. So, but let's just stick with 6 and 18 milliamps. So we're running 24 milliamps in total through this. We're wasting 18 and 6 here. Now, in a failure condition, and by the way, I didn't draw it in here, but this is of course the cap that keeps the B+ stable. So this is what you normally, what you have your capping, reference to ground. I'll just draw it in here. But it's the same function. This keeps the B+ for this driver state stable. Now, if for example this tube drops out, let's look at the failure condition first. What happens now is that instead of 18 milliamps, we're getting 24 milliamps running through here. So the whole current goes through here, which means that the voltage over this resistor increases a little bit. So it increases by a third. So that means we're going from 95 to about, say, 125 volts. And that 125 volts, you know, with the circuit being like this, 125 gets over here. So we're still at 125. We're sort of at -5 volts bias for this tube. And that's okay. So that means that the current through this tube will increase a little bit. Now let's say the current through this increases by a third. So in case of the 2A3, say that we had a 2A3 here, it's going to increase from 45 milliamps with a third higher. Say it goes a third higher. This is going from 130 to about 165, which means our bias, after the current increases for a third, our bias will be again -40, completely stabilized. So with this sort of increasing and that increasing a little bit, yes, the current will go up with a third, but then the complete circuit is stable again. Just by the way that this dropper resistor is still in place and still is dropping voltage just a little bit higher, and this stabilizes reasonably very quickly. So now we got a situation where yes, instead of 45 now amplifier is conducting 60 milliamps, but that is hardly impactful. So we can actually say that this variation of the circuit is actually completely stable, far more stable than the Loftin White, and you almost in no situation will this circuit get out of hand. Now it is a little bit dependent on how much surplus current you dump here. The more you dump, the more stable that voltage is. So there we got our fourth very stable circuit. Now this circuit also has a dynamic advantage, a little bit similar to this one. And again, it has to do with the supply impedance for your driver stage. When we increased the current and we added this bit, so we started 4 times, getting instead of 6 milliamps, we're now drawing 24 amps. That means the supply impedance to this circuit is a quarter of what it used to be. That means that this capacitor, if it's charging from a cycle where it's drawing power, it means it only takes 1/4 of the time in a charging mode. After that it will be fully charged again. So that means that the sound of this type of amp will change a little bit. And it's not dramatic, I've noticed, but it is noticeable. And the more and the earlier you have good dynamics in your amp, if you lose them here, you're never gonna get them out of your amp. Now a lot of amps are of course current limited in their later stages, but I can already tell that this construction in my amp actually and playing with this actually had an impact on the overall dynamics. Now this being a simpler amp and having very high currents available was actually better, but this is very close to it. And so I think it's a quite nice thing. You get more dynamics despite dropping current, because a lot of people would say, oh no, you never drop your B plus for nothing. You know, get your dropper resistors out of your B plus. But here actually why it works is because you just get a lower supply impedance to your driver stage. So despite the load line being relatively flat compared to an output tube, it still has an impact. You still have some milliamps swing usually, and it just helps. So that's the fourth circuit. That sort of concludes this video. As said, I'm not really saying much about the audio and the compromises that you make with direct coupling. Everything has a price in audio, but if you're on that part, you want to try it, these are 4 things for you: a goodie bag, things to think about, solutions. So I hope you enjoyed that bit. I hope that this is useful. If you have any questions or on the compromise, maybe there's another video in here for this type of subject. The one thing that I've personally noticed is that you get a lot of second harmonic cancelling when doing direct coupling, more than usual, I found, which changes the sound character. It depends on the tube combination chosen, but still you get very good cancelling of second harmonics, which can give the amp a more neutral, a more clinical feel if for example the third harmonic starts dominating the second. So it will definitely change. In my experience, it changes the sound character of the amp. But if you're after that or you're after measurements, it's a very good option because you get cancelling. Your THD will drop, but your distortion spectrum will also drop. So that's it for this video. Thank you for tuning into my channel. As always, I hope to catch you in the next video, and until then, have a great day, have a great night, have a great week, and yeah, I hope to catch you soon.